Hi, my name is Ayfer Ozgur. I'm from Stanford University. And in this talk, I would like to tell you a little bit about achieving communication efficiency, privacy, and accuracy simultaneously in distributed or federated learning type settings. And this is joint work with my PhD student, Wei-Ning Shen at Stanford, and Peter Kairos from Google. Okay, so we're interested in federated learning. We want to train a centralized model from data that's distributed across a large number of nodes in a network. And we now, it's now well understood that two important challenges in these kind of settings are achieving communication efficiency and ensuring privacy for the user data. And in this talk, we will approach these problems from a distributed estimation perspective. And here you can either look at statistical estimation settings or so-called distribution-free settings. So for statistical estimation, we will assume that we have n samples generated IID from a distribution parameterized by some unknown parameters theta. And each node here observes one sample from this distribution. And then the goal is to estimate the parameters of this model at a central node. But now all communication here is subject to bit constraints and privacy constraints. And we'll take a minimax approach. So assuming that we're given some loss function here that measures the error we make if we estimate theta as theta hat. And if you give me any strategy, any estimation, this would be a joint communication estimation strategy for the setting. I will look at its worst case performance over all possible realizations for these parameters. And two simple canonical examples here would be discrete distribution estimation, where we assume that this underlying distribution, this is an unknown discrete distribution, and the only thing we know about the distribution is the alphabet size. So let's say, or let me say the alphabet. Let's say the alphabet is the numbers from 1 to D, and then the goal is to estimate the probability of each symbol in our alphabet. Or another kind of classical example would be Gaussian mean estimation. So here you assume that these are, each sample here is a d-dimensional vector, and it comes from a d-dimensional Gaussian distribution with, let's say, identity covariance matrix and some unknown mean, and the goal is to estimate the mean of this Gaussian distribution. And one can look at also the distribution-free versions of these settings. So here, we don't want to make any assumptions on any probabilistic assumptions on how the data is being generated. So instead, we just say we have some data that's distributed across these n nodes, and at the central node, we would like to compute a certain function of this data, which will typically be of this form. And again, we will adopt this minimax approach. For any given strategy, we will look at its worst case performance over all possible realizations for this data. And here I have an expectation. Remember, this time I don't have a probabilistic assumption on my data. The expectation now is we will in general allow our strategies to be random, and the expectation is over the randomness in our strategy. And the two examples, two kind of canonical examples for this case, corresponding to the two examples I gave you in the previous slide, would be, the first one would be empirical frequency estimation. So now let's say this data here comes from a discrete alphabet, let's say numbers from 1 to D. I have some samples here that lie in this set, and I just want to estimate the empirical distribution of my samples, the empirical frequency distribution of my data. And if you actually take this excise each sample here to be encoded in a one-hot fashion, you can represent the empirical frequency distribution as an average of these one-hot encoded sample vectors. And the second case would be distributed mean estimation. So here we assume that each sample here is some arbitrary d-dimensional vector lying in this d-dimensional unit ball. And the goal at the central node is to estimate the empirical mean of these d-dimensional vectors. And of course, we want to do all this under bit constraints on the communication and privacy constraints. And how do we model these constraints? So as I mentioned before, we will allow the mapping here at each node to be randomized, in which case you can represent it as a conditional probability distribution, which tells you how to map given xi. Each sample is mapped to some, let's say, arbitrary output alphabet by this conditional distribution. And now if we have communication constraints, we would want to restrict the cardinality of this output alphabet, say by 2 to the k, in which case each symbol in this output alphabet can be represented by k bits. And we would be at most communicating k bits per sample per node here. And how do we model privacy? Well, we'll use the notion of eps-local differential privacy. So when we want this communication here to be private, we will require this conditional distribution to be such that the probability of any output symbol doesn't change too much with the input symbol, in the sense that this ratio here for any y, x, and x prime is bounded by a constant e to the epsilon, and this ensures that our communication doesn't leak too much information about the true sample at the corresponding node. There has been quite a bit of work in this direction in the recent literature. This is an incomplete list, including some of our own work. The point I would like to make here is that prior work usually focuses on one of these constraints at a time. Okay, there are good privatization schemes for these kind of settings in the literature. There are good communication efficient schemes, but typically in practice, right, we would want our strategies to be both private and communication efficient at the same time. And in the rest of my talk, I would like to argue that you cannot achieve communication efficiency and privacy by just taking the optimal privatization mechanism and concatenate it with the optimal compression scheme. You can do that, but if you do that, your performance, your accuracy will be very suboptimal. And you can do much better if you start from first principles and design your strategy more carefully to achieve both communication efficiency and privacy at the same time. And okay, to do that, I would like to focus on distribution estimation, because that's a simple, that's simple and at the same time has been quite widely studied in the prior literature. So to recap, so our setting here is the following. We have an underlying unknown discrete distribution. Each node observes an IID sample from this unknown distribution. And we would like to communicate these samples to the central server, which wants to estimate this unknown distribution. And the error metric I will focus on in this talk is the L2 error, but our results also extend to other error metrics, for example, L1 in this case. Okay, so let's look at the setting first under separate communication and privacy constraints, and this has been studied in the prior literature. For example, this is a paper we had in 2018 where we studied this discrete distribution estimating setting under communication constraints. And here you can show that the minimax risk, the optimal risk will be of this form. And now if you compare it to the case where you don't have any constraints, so you just have these NIID samples available to you as to the central server as they are, then the risk would be 1/n. And you see here that now when you have a communication constraint, especially when k is small, the number of bits you have per sample is small, your risk will be d/n instead of 1/n. So there is a factor of d penalty in the error here that comes from this limitation in your communication budget. The strategy, this setting, same setting, discrete distribution estimation, has also been studied under privacy constraints. So, for example, there is this work by people from Google here from 2016. One privatization mechanism you can apply here is this randomized response, where you simply take your sample and you either send it as it is to the central server, or you switch it to one of the other d-1 symbols uniformly at random with some probability. And the probabilities have to be adjusted to the privacy level you would like to achieve. Turns out that this is not, this doesn't achieve the optimal accuracy in all privacy regimes, but there's, for example, this follow-up work by Ye and Bark where they propose this idea of subset selection, and this can be shown to achieve the optimal accuracy privacy trade-off. And for this particular problem, discrete distribution estimation, it's given by this expression here. And if you look at this expression, you see something similar as in the case of communication constraints. So when you see that when epsilon is small here, and epsilon small means high privacy, then your risk is like d/n again instead of 1/n. So there is this factor of the penalty in the error. What if you have, so now we know the optimal communication efficient strategy for this discrete distribution estimation problem. We know the optimal private communication strategy for the same setting. What happens when you want both of these things, when you want to be both private and communication efficient? One kind of simple idea here would be to take these optimal mechanisms, right, and to just apply them back to back. First, privatize your sample with the optimal privatization mechanism, and then compress it with the optimal compression mechanism. But turns out that if you do that, you will suffer a double penalty, once for the communication constraint, once for the privacy constraint, and once for the communication constraint. So your risk now will be like, will scale like d square instead of d in the case when you have only one of these constraints. Turns out that this double penalty here is not fundamental. So you can actually design your scheme more carefully. And this is what we do in this paper. And you can show that this minimax risk here is achievable under joint privacy and communication constraints. And if you look at this expression, you see that you don't have this d squared term anymore. You don't have the double penalty. And indeed, your risk here will be dictated by the more stringent of the two constraints. And the less stringent constraint can be satisfied for free. Okay, you're not penalized twice anymore. And this also, for example, tells you that in this particular setting, if you wanted to achieve epsilon differential privacy, then you don't need more than epsilon bits to achieve the optimal accuracy. And here I talked about this discrete distribution, the statistical setting, but the same result can be also extended to empirical frequency estimation, to the distribution-free version of this setting. Okay, I'll skip the details of the scheme. As I said, you need a more carefully designed scheme that's designed to achieve both privacy and communication efficiency at the same time. You can also show a similar result for for other settings. For example, for this, recall this distributed mean estimation problem, where we assume that we have this n samples, and now these are just some arbitrary d-dimensional real vectors in the unit ball, in the d-dimensional unit ball. And your goal is to estimate the empirical mean of these vectors. And this setting has received quite a bit of interest over the last couple of years because it serves as a basic building block in many distributed optimization tasks, for example, in distributed stochastic gradient descent. And this problem has been studied under separate privacy and communication constraints. Just like I said before, if you take these, we know the optimal strategy here under privacy, and we know the optimal strategy under communication constraints. But if you take them and if you concatenate them, if you apply them back to back, then you'll suffer a double penalty. For example, there is this recent work here, BQSGD. Actually, this is the only work I'm aware of in this setting that looks at both privacy and communication constraints at the same time. And they have one scheme here that aims to achieve both at the same time. The scheme is designed in such a way that it's applicable only in a certain epsilon and certain K regime, certain privatization level and bit budget. But in this regime, you see that it achieves this, the error it achieves is like d square over n. So this is similar to the baseline where you concatenate the optimal privatization scheme with the optimal communication efficient scheme, and you suffer this double penalty. Whereas what we're able to show is that if you design your scheme more carefully, so now you can come up with a scheme that's optimal for any privacy level and any communication budget. And the optimal error turns out to be of this form. Again, you don't have the double penalty anymore. And your error is dictated by, you see the minimum here between epsilon and the case. So the error is dictated by the more stringent of the two constraints, and the less stringent one can be satisfied for free. Maybe I'll conclude by just showing you a few graphs. So here we experiment with with this distribution estimation setting, and here we generate our samples from a geometric distribution. So I mentioned the subset selection algorithm. This achieves the optimal privacy accuracy trade-off for the setting, but you see that it requires 63 bits per sample per node to communicate each sample. Whereas the scheme we designed, which we call it the recursive Hadamard response, because it critically builds on the recursive structure of Hadamard matrices. This can achieve somewhat, a close performance, but now by using only 3 bits per sample. Okay. Okay, and maybe I'll show you one plot related to the mean estimation setting. So here, if you take the optimal privatization mechanism for this mean estimation setting, this is this blue curve. This achieves the optimal accuracy privacy trade-off. But you see that the number of the communication, the number of bits it needs per sample is like 2,000 bits per node in this particular setting for this set of parameters. But our scheme can achieve a similar performance by using only 5 bits per sample per node. And now, if you take this optimal privatization mechanism, the output of this optimal privatization mechanism, and you compress it to 5 bits, you force it to 5 bits by using the optimal compression algorithm, then you see that the performance of this concatenated approach will be much more worse than that achieved by our strategy. So this is what you achieve with concatenation, or I call it separation here. And this is the performance achieved by our scheme. This is the error as a function of the number of dimensions D. And you see that the performance gap gets bigger and bigger as D increases, precisely because the error of this scheme, of the separation approach, scales as D square due to the double penalty, whereas the error of our scheme is linear in D. And I guess this is all I would like to say, so I'll be happy to answer any questions in the Q&A session. Thank you.